Alright, what else can we do with fluid statics here? Let's take a look. First, let's consider a spillway, for example. This is basically some type of concrete, and over here we have a water level. Now, let's say the water level is at the very top, and let's say this is 10 foot. The first question you might ask is, what's the load on this? Is this going to hold? Because there's a bunch of houses over here, and you don't want them to get washed out. So the first thing you want to do is resort to something you've seen before, and that's statics. Let's deal with the fluid part of it. We know that the pressure is equal to gamma H, so if we go down at H, the pressure at that level is equal to the gamma of the fluid times the H. So now let's take that to the extreme here. We know that this is a linear profile. What I mean by this is a constant for the fluid, and this varies. So the deeper we go, the higher the pressure. So if we're talking about gauge pressure, this pressure at the top, as well as all along the top, is 0. A lot of times in textbooks they'll put a triangle here to denote a free surface, and that basically implies that the gauge pressure there is 0. So let's take a look at this. If you look at the profile, it's linearly varying. So you might see something like this. So suddenly the concept of statics becomes pretty important here. Let's say we turn this thing sideways. Let's first, before we turn it sideways, let's say we're interested in the load on this per unit width into the page. So if we're interested in that, we could turn the thing sideways. So now this thing would look like that, and here would be the spillway, although you don't need to draw this part anymore. This would be the 0 location, and you would have something like this. Technically, this would look a lot like a cantilevered beam, cantilevered into the ground here, and free at the top. And we're not interested in the deflection here, but we are interested in the load. Now, if you did a side view of this, or tried to do a perspective of it, give me a few minutes to do that, you would see that this would be 1, this would be 10, and since it's easier to draw it in the other direction, now I'm going to put the load on it. The load, this being the top, the load would kind of go like this, up like this, and it would come down this side, and it would be what's commonly called a pressure prism, or basically a load here. Now, since this is constant throughout, you could turn this around. In other words, let's just work the numbers here. On this end, the pressure is equal to 0. On this end, the pressure is equal to 10, and to make my life easy, I'm just going to say that's 50. So it's not water, but it's a little bit lighter than water. So that's gamma H, or pressure, is equal to 500 pounds per foot squared. So that's just 50 times 10 feet here. And if you want to see where those came from, they came from here and here. Now, in statics, you were used to seeing a load per running foot. You know, so much pounds per foot. And then you started working the problem based upon that. Now, the fact that this is 1 in depth means that I can go in here and take a small strip across here and look at the pressure. Well, first of all, this strip length is 1, so if I say that's dx, then the area that this thing contacts is 1 times dx, or 1 foot times dx feet, which means that I can just simply redraw this. It looks exactly the same. It's just a beam, which now it's 500 pounds per foot instead of foot squared. Why? Because it was 1 foot deep. So now you're looking at exactly a statics problem. You've got this thing applying a moment here and a load here. Now, usually we're not interested in finding those in the early going, but we will later. So you figured this out long ago, that this is equivalent to a diagram in which, you have to remember, this is 10 foot long, so this is 10/3 over to here. The load here was what? 500 pounds per foot times, now this is the case, if you remember, where you had this part of the load is not existent, so this is taken off, and this load's half of that load. So 500 times 10 feet gives you the load it would be if it was a constant across the top, but you only have half of those, or you have 5,000 divided by 2, or 2,500 pounds. At this point, you could go through your statics and figure out the moment here and the load here. Well, first, of course, the load's going to be 2,500. This moment's going to be that times the 10/3. So you can see the concept, the name here, fluid statics. Fluid statics, the name is prevalent throughout here, and there are other cases that are not beam looking that might trip you up. And let me take a look at one. Let's say we had a cylinder, or let's just make it easy. Let's make it a square. You fill it up with water. Say you attach a chain here to something like that. And then, let's see if I can do a decent job of drawing. It's attached to, say, another square down here. Okay, give me a minute. And say it's welded all along this edge. And you want to know, well, what's the load of this thing carrying? So it's, remember, it's filled to the top. So let's say this is 2 by 2. So that means this is 2 and this is 2. And then say this is 10. Or, well, if that's 2, let's make this 2. And this distance be 4. And this distance be 4. So I didn't draw it to scale. So that gives me back my 10. And we want to know the load of these welds. Well, first, let's draw the weight of the water in the bottom part. The weight of the water in the bottom part is just going to be gamma times the volume of it. Well, let's see. Let's take a look. That's 10 by, and I'm going to make my life easy again. Gamma is equal to 50. 10 by 2. Oh, I didn't state the height. Let's make this 5. 10 by 2, so it's 10 by 2 by 5. Oh. And then that's the volume, and then multiply that times 50. 5 times 2 is a 10, then another 10, that'd give me 100, and then multiply it times 50. I could just move things around, so I get a weight of 5,000 pounds. Now, let's go also and take a look at the top of this. Okay, this thing has a weight associated with it here too. Okay, we've got some cables that are coming up here and pulling with a tension here. I'm going to assume the weight of these things are all zero. So in other words, the containers have no weight. So the tension is going to be equal to, okay, now I've got to figure out this weight. Same equation, different volume. 50 times what's the volume there? 2 by 2 by 2. So 2 by 2 by 2. 2 times 4, 2 times 2 is 4, times 2 is 8. 8 times 5 is 40, but you got another term, so that's 400 pounds. Now, this is a concept that's somewhat similar to statics. That we're going to talk about, and that is in statics. Let me refresh that. In statics, you may have had a beam that's supposed to be a straight line. Looked kind of like this. Then what you did is you came in here and in your imagination you sliced it right there. Now what you did when you sliced it is you changed the load. Whoops, supposed to be a straight line again. So there's actually another part of this beam sitting over here, and in your imagination you split this. Well, you have to maintain on the portion that you had some of the forces equals 0 and some of the moments equals 0, and you put the resultant load back in here. So you had to put something like that because this had to be the same value as that to offset it. But now you really don't have the summation of moments. You have the sum forces being checked. So now you have to sort of put a moment back on here. So in your imagination, the point is, in your imagination, you would go and slice something, even though you physically were not slicing it. You did it in your imagination, and then you turned around and put the loads back on it that would be there to sustain it. Let's use that same concept here. What we're going to do is I'm going to take a look at the lower portion. I already know it's 5,000 pounds, so I'll put it on there. I know that this thing is pulling up with, say, the force of the welds. So, and I could put this over 2 and just say, I'll do it that way. Force weld W over 2. Here, I'll just do it that way. FW over 2, FW over 2. Those are the force of the welds. There's another load here, and that is an equivalent. Let me see if I can get it in here. Make it look nice. This is a pressure load. That pressure is equal to gamma H, which is equal to 50 times the depth here. That depth happens to be 2 feet. So it's 100 pounds per square foot, but it's applied over a cube here, or not a cube, but a square. It's a 2 by 2 square, so the equivalent force there is equal to 100 over a 2 by 2. That's 4, so that's a 400 pound force shoving down. Now in my mind, here's what I did. As I went in here and I just split this right here. Whatever loads are being applied to the fluid and the side of the solid, the welds there, I put in there. Now, what that means, and I didn't do a good job of this, I should have thought ahead. I could have created a member that looked like this. But the load here that I would have sliced away would have still been 2 by 2 if this was 2 by 2. It would have still been 400 pounds. Even though there's more weight up here on the side, it was carried by this side member. And maybe I'll look at that later. But without being too confusing, let's stick back to our problem. So if I go over here, sum of the forces in the y direction, because that's what I'm mostly interested in. Here I've got a minus 5,000 pounds, and then I've got plus the force of the weld, and I got this thing shoving down, and that's minus 400 pounds. So, and that's supposed to be equal to 0. So I got the force of the weld being 5,400, or the force that the weld's having to hold is 5,400 pounds. Now let me state what I was talking about before. Let's say now I had a member that looked like this. Okay, so it went back, went across. Its measurement was, okay, give me a second. Okay, so let's say we pick the same measurements. 2 across here, 4 across here, 4 across here, 2 going straight up. Okay, 2 going straight up. What else did I forget? I forgot the 2 here, 2 here, 10 here. But let's say these things are tilted over at 45 degrees, just to be easy for myself. Then I contend that this free body diagram is exactly the same. But yet, you see something's different. Let's look at the top member and we'll see what looks different. The top member alone looks like this. Okay, let's do a free body diagram on the top member. Now, I sliced it. You have to remember, I sliced it right across there, and I'm taking a look at it. But this time I'm looking at the top member. First of all, I've got a load across the bottom. That happens to be the total force is that 400 pounds. Why? Because it's still 2 foot deep. I have the weight of this stuff in here being 400 plus pounds. Why? Because the volume now includes, here, let me erase those, use a different color. The volume now includes these portions over here that were not included a second ago because the geometry wasn't this way. So in lieu of not calculating that, I'm just going to call it the weight of 500 plus delta. And delta is not necessarily small here. So what do I have that's different? Well, first of all, let's draw a diagram of the force along this edge. Okay, first of all, the pressure on the top is 0. So, but we get down here, and this is, what was it? Gamma times height, or 50 times 2 foot. So this is 100 pounds per square foot. And actually, you get a load that looks like this up the side. You also get a, if I can make it look about the same geometry, it's the same geometry running up that side. Now, what can you say about that? If you take a look at just the force, pull a force away, look at it, and tell me what you think the components are. First of all, this can be broken down to an equivalent load that is existing 1/3 of the distance up, and it looks like that. I contend it has a component that way, and it has a component that way. This component on both sides, if you add it up, it's the same thing as that delta. So you can have a larger weight. It just so happened that that happened to be 400 pounds. It also happened that the weight of the fluid in there was 400 pounds. But it does not have to equal. This brings us to another contingent. Now, this is something you should have realized from one of the earlier lectures. You know, force is equal to pressure times an area. Force has to have a coordinate direction, has to have X component, Y component, Z component, whatever, so too does the area, because this is just a scalar. So every time you look at this, you look at the geometry, you can start seeing what's going on here. So now let's focus in on something that looks just like this. Okay, here, let me just draw a line and say we're going to focus in on something that looks like that. However, we're going to put it in a different drawing. Here's a chunk of concrete. Here's a hinge. I like 45 degrees. I can calculate the sine and cosine pretty easy. So there's a gate. Here's another piece of big concrete. What you'll find is that this load is, we'll just call it not F, but let's call it R, reaction load, is the force that the concrete puts on this gate if we fill it with water back here. Let me redraw that. Yeah, I'm going to make my life easier again. It's not water we're going to use. It's something a little lighter than water. So you're sitting there looking at this. You fill it with some sort of fluid which is kind of light, lighter than water, and you want to know the load on this. Let's say there's a person down here, stares up at that thing, and what this person sees is, here, let me shorten this. What this person sees is a square gate. Not square, but rectangular. Let's say he sees it 10 foot this direction, so it's 10 foot like that, and says he maybe sees 5 foot there. I may move that out of the way. You also need to know what the depth here is, so I'll just make it 5 foot as well. Well, maybe better make that 4 foot. Keep the numbers separated here. Okay, now the question is, what is the reaction here? That's going to be your goal here. This is going to be a hinge, so you know there's going to be no moment produced by that hinge. That's your hope there. So you redraw this on a free body diagram, trying to do the best you can, and what you find is, okay, first of all, there's a preload on this top, and that preload is the pressure is equal to 4 foot H times gamma, or gamma times H, 50 pounds per foot squared. So that gives you 200 pounds per foot squared. This is foot to the third, sorry about that. That's the pressure here. Pressure on the other end is higher because it's deeper. You go that much deeper. Oh shoot, I also have to state here that if you drew a line here, let's draw a little thin line, red line here. This thing is 45 degrees. Alright, so here's my diagram. Okay, so what's the pressure down here? Pressure is still that 50 pounds per cubic foot times the height. Well, the height now is 4 foot plus this distance. Well, what distance is that? Well, let's break it apart. Okay, I'll come in here with a light colored red. So you've got a 45 degree, it's supposed to be 45, it doesn't look exactly like that. This is 10 foot. What is that? This squared plus that squared got equal to that squared. So say, I don't know, call it L. L squared plus, L squared square root's equal to 10. So you multiply that, you make that 100, you get 2L squared. L squared is equal to 100 divided by 2. And then you say, well, L is equal to 10. 10 over square root of 2. Oh, let me rechange my... So this turns out to be 10 over square root of 2. I can use a calculator and solve that in a minute. Or I can just keep going here. So you also have that this thing is 5 foot into the board. So now you want to find the... Remember, you're still looking for the reaction load. And you could put in here, and I'll put it in, say, red. There's a hinge X load, and there's a hinge Y load. Now you have to remember there's no moment around the hinge, hoping that there's no friction on it, which is one of the things that you're going to have to assume. Now let's just turn this thing sideways. And then it becomes a problem just like statics. Oops, not a good straight line. So you're looking at something like this now. Now, there's your reaction. Here's the hinge, one hinge load. Here's the other hinge load. We'll call this Y and X now. These are not the same because I rotated the thing around. Now the question is what is the real load over here? Now you have to remember, I did this and it's feet squared. What you're used to seeing is per running foot. So the load on this end is 200 pounds per foot squared times this depth right here, which is 5. Now here's the key. You can do this as long as you take a delta x here, or say call this a dy, and this length stays the same as you run up and down here. So you can run up and down any particular location. The length is the same, meaning it's either a square or a rectangle. Okay, since it's 5 foot down, you end up with that. 200 times 5, or 100 pounds per running foot. Okay, on this end, you could split this apart, and I think I'll do this real quick. If I do this, I get 1,000 pounds per foot plus 10 over square root of 2 times 50 times 5. What I've just done is I've taken this times that, okay, this times that, times my running 5 foot here. So now I got to resort to the calculator. So what I've actually done here is this, is I've said to myself, I've got a portion here which is 1,000, and then I've got another portion here, but I don't know what that is yet, but give me a second here. 10 times 50 times 5 divided by square root of 2 looks to me like that number is around 1767.7669. I'll keep those digits for a moment. And now my drawing is cluttered, so I'm going to reproduce it again. There's my reaction. Hinge Y, hinge X. I've got this load. this thing is 1,000 pounds per running foot. This is 10 foot across here. And then I have a triangular load dropped right on top of it. Of course, the triangular load on that end's nothing. And then over here, it's 1767.8. Might as well just make it 8. Now that you have this statically done, you can redraw the thing again. Reaction, hinge Y, hinge X. Now you drop a load right there in the middle. 1,000 pounds per running foot times 10 running feet. 10,000 pounds, if I can multiply that quickly. Then I got one that's hanging over here, 1/3. Now, you've seen that 1/3 rule. So this distance right here is 10 over 3. The value here is 1767.8. And this is, I should have put this in here, pounds per running foot. So I take this, I multiply times its 10, because that's the length here. And then you have to remember, I don't have this portion of the load here. Okay, let me go back. So I got a half of that, so I can put a half there. And let me work on the calculator here. And I get about 8838.83 roughly pounds. Now my units here, this is pounds per running foot. That's my foot, and that's my ratio that cuts out that yellow part there. Now I've got my loads, I've got my locations. This is 5, by the way. And I have 3 unknowns. However, as always in here, you can sum the moments about the hinge and you can work them out. Sum the moments about the hinge, making that plus, say, for just no particular reason, r times 10 minus 10,000 times this distance, which is 5. So what I've done is, there's my 10,000, there's the distance it's away, and I'm going to run out of space, so I'm going to do my 8,838 and change times its distance. But its distance is this distance, which is not 10/3, but it is 10 times 2/3. Yeah. All right. So that's equal to 50,000. That's easy enough to figure out. And then this I have to work on. Times 10 times 2 divided by 3. 58,925 and change. Add that to 50,000. And then divide that by 2. Gives me my reaction being roughly 54,000. Oh, sorry. Divided by 10. Okay, so I divided by this by 10, so that'd be around 5,000, and around another 5,800 gives me 10,892.55 pounds. So at this particular point, if you were given any particular problem at any angle, you should be able to solve that. Example might be, let me give you some examples and you can maybe go work them and see what you guys get. Let's say you had a spillway that was at, say the hinge was down here, and say it was at 30 degrees. So the hinge is down here. Here's a bunch of concrete. Here's a concrete support. say the distance from here down to here is, say, 10 foot. Say this is a 20 foot by 5 foot into the page, meaning that if there was a guy down here looking up at it, he would see something that looked like this, 20 by 5 foot. So if he's looking up at this, that's what he sees. Fills it up with, say, some fluid. We'll just stick to water since you're working it, not I. I put that down there, and I want my eventual question is, what's the reaction up here? Quick run through. All you have to do is you put the load on here, find out the depth down here, find the pressure here, find the pressure down here. It gives you this pressure diagram. Notice that when I draw this, it is always perpendicular to the surface, as it should be. Then you can replace this with the hinge loads, turn it over on its side. What you're looking at is the reaction over on this end. You can break it into its two portions. And you got your hinge load here, hinge X and hinge Y. Oh, hinge Y and hinge X. Here's your gate. And from here you just take off and run. The only complication that you had here was that the hinge was on this end, that the angle was 30 degrees. So now to find the depth across here, if you were looking for the depth from here to here, this depth would be related to that 30 degrees, not the square root of 2. So this depth right here that you're going to use in your equation that you did up here, which was, what, 10 over square root of 2, changes. Now there's a cosine or sine here associated with an angle. And so you can just keep drawing as many of these as you want. They all look the same. Here, draw another one. Say we tilt it this way. Say we do this. Okay, let's say put a hinge, maybe tilt it over at 5 degrees. Say we put the water, say we're pushing here with some reaction load, and say we put the water at the very top. Here's the concrete. This thing is 5 degrees. What do? You take off and you put your load here. Whoop. Since the water's touching the top, it's a triangular load only. Now you start breaking it away. Look at your free body diagram. You get the same thing. Here's your hinge. There's the hinge. Got a load down here. Got no load there. And then you take off. How many others can you look at? Well, I don't know. Well, let's look at this. Let's say somebody puts, now this is a good problem that might end up on a FE exam, and actually has ended up on some stuff like that before. So you have two fluids here. Gamma is equals 62.4, and over here gamma is equals 62.4. Obviously this is heavier, so you're going to have something that looks kind of like this. That's a piece of concrete. As a result, you're going to have a reaction load here. Let's say we move the elevation here up just a touch to say right there. So let's say this is 1 foot and this 10 foot. Say this is at 30 degrees. Now, let's start breaking this apart. Look at it real quick. Now, this problem on an FE exam, they expect you to answer this in a matter of seconds. So your first thing is, let's look at the top side. I'll draw my R. I'll draw my 1 foot pressure to here. So I've got a little 1 foot pressure to here. It increases down. Okay, so I'm just going to draw my straight across first. And then I'm going to look at the increase of pressure from down this elevation to this elevation. So you add the little triangle onto here. Not a great drawing, but what do you expect? Now you look at this side. Now this has a 10-foot down on this side, so the pressure over on this side is quite a bit higher than the pressure on the other side of this gate. So the diagram should look kind of like this. Now, as it turns out, if you look at the left side and you look at this distance, say D, it's the same as if you were on the right side. That distance on here is the same as that distance. It's kind of like saying, let's draw a triangle. Let's look at it like that. This is 30 degrees. Let's draw a triangle. This is 30 degrees. This is, say, 10. What's the distance here and what's the distance here? Well, they're the same. The same as the distance here is the same, but we don't care about that. So this distance on the right end is the same as the distance on the left end. As a result, whatever this pressure distance here is the same as it is on this side. I have to talk about that because I'm not a good enough drawer to make you believe that. So these are the same. First inclination would be work hard for hours and hours to find every one of these loads and then do a free body diagram. However, if you took a quick look at this and you notice that this load, or here, let me use this portion of the triangle is exactly offsetting to that one. And this part will slice out a portion here. So your equivalent free body diagram would look like this. Nothing more than a flat load sitting here, in which if you looked up here, the difference between this number and that number is 9. So that would be 9 times 62.4. That's the pressure right there. Pounds per foot squared. And you'll have a distance here and a distance into the board. And just like that, you can put your hinge loads here however you want. Some moments about here, and suddenly you find out this problem can be solved in a matter of, say, 60 seconds or so. But you had to be able to recognize that these portions of the load will cancel. So with that, I've run 43 minutes here. That's the equivalent of what you would get in a regular class. And so I think what I would expect you to be able to work is a problem that sat like this. Just imagine any angle. It could be anywhere. It could be water on the right or the left of it. It could be hinge on the top or the bottom of it. All you've got to do is put the equivalent loads pressure that based upon pressure is equal to gamma h down to those locations and start working a statics problem. And that's it.